I will first start by a brief introduction on CERN. You have already heard many things on CERN history from the previous speaker. I will concentrate most of my time on the LHC program without ignoring completely the non-LHC program, including the nuclear physics program. I will say a few words on that, and I will conclude by a brief summary. So CERN is an international laboratory which has been created for the purpose of carrying out an agreed program of research of a pure scientific and fundamental character relating to high-energy physics. This is in the Convention of 1954. High-energy physics, or particle physics, it is really the aim to discover what the universe is made of and how it works. In other words, in what are the elementary constituents of matter and what are the fundamental forces that control their behavior at the most basic level. To do this research, European countries are joined their force, and this is the famous plot where you see the 20 member states as they are now. I always look to this plot with some emotion because in our countries, France, Poland, UK, which have so much suffered in the first part of the 20th century, to do science together is certainly much better than the war. As the highest priority of CERN is to prepare, to develop, to install, to commission, and then to do physics, the Large Hadron Collider. This Large Hadron Collider will be the last part of all a chain of accelerators which start in the 50s by the proton synchrotron, the PS, which then was, to which was added in the 70s the super proton synchrotron, and the super synchrotron now will be completed or will be supplemented by the Large Hadron Collider. The previous machines still exist. They are used as injector, so the particles get some energy in the PS, they get more energy in the SPS, and at the end they obtain their final energy in the LHC. But from the PS and the SPS, there's still some physics which is feasible and which have some special interest on which, and that I will comment in a moment. Also interesting, the Large Hadron Collider will be installed, or is being installed, inside of tunnel, which is 27 kilometers of circumference. It is installed well below the Earth. Typically, in some places, it's at the level of 100 meters below the ground level. And in this tunnel, before, up to the year 2000 was installed the LEP, the E plus E minus collider. And the energy which was available in the collision at LEP was 200 GeV, so giga electron volt, while for the Large Hadron Collider, the energy will be 14 TeV, so tera electron volt. And even more, when one day, instead of lead, we will put in the Large Hadron Collider lead nuclei. So remember this value of 14 TeV for the energy available in the collision of protons at the Large Hadron Collider. If you go now to CERN in the tunnel, unfortunately, you don't see yet these things. You will get it, hopefully, not very long from now, but it's just being installed, and we have some minor difficulty, but which takes time, or installing the so-called cryogenic line these days. But one day, it will look like that, and the main component of the accelerator are dipole magnets, which are 15 meters long, which are superconducting magnets, and which are cooled down by liquid helium at the temperature of 1.9 Kelvin degrees. Here you have seen this very sketchy way of the SPS, of the LHC, and I just introduce you the 4 names of the experiments: Atlas, Alice, CMS, and LHCb, that I will describe in some more details in a few moments. And these experiments are also being installed this day, but they have just started the installation. And this you can see here, for instance, for the cavern of the Atlas detector, which is about 50 meters long, 30 meters in width. the beam one day will arrive from this place, and so far you essentially see a lot of pieces to support the detector. It's not yet installed. But everything should be ready by summer 2007. Why do we want to accelerate always particles with more and more energy? This comes essentially by this famous equation you have all learned at school, which show the equivalence between energy and mass. And for instance, at the Large Hadron Collider, the total energy which will be available in the collision is 14 TeV. And this 14 TeV will be used largely to create new particles. And typically, with this 14 TeV, we hope that we will be able to produce new objects which have a very special interest, which could have a mass of 1 or maybe even 2 TeV, so tera electron volt. And this will be a machine at the energy frontier. It means that no machine so far is capable to create particles which are heavier even than a few hundred GeV. Now, with the Large Hadron Collider, it will be possible to go at the level of 1 or 2 TeV. To go in somewhat more details on the physics that the Large Hadron Collider would like to do, I would like just to remind you a few basic things. You have already seen this plot where you go from the molecule to the atom to the protons. Interesting that the proton is not an elementary particle. The proton is a composite particle. So inside the protons, you have quarks and gluons. All the matter, or the stable matter of the universe, is made of 4 basic bricks. The quarks, up and down, that you heard before, and also the leptons, the electron, the one which is around the nucleus in an atom, and a partner of the electron called the neutrino. I will come back on the neutrino a bit later on. The neutrino has no electric charge. He only interacts very weakly, and it belongs to the same family that the electron, called the leptons. Actually, what we have found at CERN and in a few other places in the world, that there is not only one family, the one I described before, the up and down quark, and the neutrino E and the electron. There is 3 families of quark: the up-down, the charm and the strange, the top and the bottom. And similarly for the lepton, there is 3 types of lepton. There is an electron, an heavy electron called the muon, and an heavy muon called the tau. And as associated to these particles, there are 3 types of neutrino. You heard from John Ellis that these elementary constituents interact between each other in a 3 different ways, either with electromagnetic force, and at that time they exchange a photon, or they have a strong force, the one which binds the quarks inside the proton, and they exchange gluons, or some weak force, and then they exchange particles as the Z and W bosons. It is the force which is the one which can describe the radioactive beta decay. Just one remark on the mass. You see, these basic constituents have still a very spread of mass. You go from the neutrino, for which the mass is almost null, but not completely. The electron has a mass of 0.5 MeV. The top is 175,000 MeV. It means that the top quark, one of the fundamental constituents, is much heavier than a proton. A proton would be 1,000 MeV. Since several decades, many facilities in the world, but especially the lab, has tried first to check whether this global model of this elementary constituent and their interactions, called the standard model, is a good model. And also if there is some place where we could go, where we could see that it does not work. In practice, all the experiments so far, and especially those at lab, which has been extremely precise, has verified that all interaction of elementary particles that we can reproduce in our laboratory are perfectly described by the standard model at the 1 per mil level. Now, let me come back to this problem of the mass. So you heard already of the Higgs particle. I'm sorry, it will be a bit technical, not this image of people at a party that John has shown, just to give you another way to look at what is called the Higgs mechanism, which is an important part of the standard model, the one which has not yet been tested. So in the simplest theory you could imagine, all particles are massless. Now it is assumed that there exists a field which pervades the universe. The field should be everywhere. And particles interacting with this field acquire mass. And stronger the interaction, larger is the mass. The field is a quantum field, and the quantum of the field is the Higgs boson. So finding the Higgs boson, which is a well-identified particle, would establish the presence of the field and would validate the Higgs mechanism. What do we know about the Higgs? First, we have tried to produce it in many places, especially at lab, but without success. But we know that it must be heavier than 114.4 GeV. And from indirect measurements, for all the experiments we have made so far, we can reasonably predict that it should be less heavy than 237 GeV. The standard model, as I said, is been fully verified by all experiments we have been able to do in the laboratory. Anyhow, we are convinced that the standard model is a low-energy approximation of a more fundamental theory because it contains too many apparently arbitrary features, too many mass, too many numbers. It's not very aesthetic, and when it is not aesthetic, usually it is not the truth. Second thing, the standard model, as I said before, does not incorporate gravity. It is the interaction you all very well know, the gravitation, and any complete theory should, of course, incorporate gravity. Third point, we also know from measurement in the sky or astronomy that only 5% of the universe is made of normal and visible matter, and the matter that we can describe by the standard model I mentioned before. So a very important question is what is the nature of the dark matter which pervades our galaxy and the whole universe? This limitation of the standard model really calls for a new physics that we don't know which one is right. There are three propositions, or there are many propositions. I can quote three of them: supersymmetry, extra dimension, string theory. What is especially interesting that all these theories which go beyond the standard model predicts that there will be some signature at the TV scale. And remember that the TV scale, it is the energy we will have in the collision at the Large Hadron Collider. If I try, maybe it's a bit audacious, but I try to put on one transparency to give you a flavor what is supersymmetry. For every particle, there exists an antiparticle. For instance, the proton and the antiproton, the electron and the positron. Similarly, supersymmetry predicts that for every known particle, there exists a superpartner particle. And what differs between a particle and a superpartner, it is a special quantity that we call the spin. So in simple words, if you take a particle, say a proton or a quark, it has some intrinsic angular momentum. You see, it turns in a way in some directions, and this angular momentum is quantified. It can have the value 0, 1/2, 1. And the difference between a particle and a supersymmetric particle, it is that its spin is differ. For instance, for the electron, the spin is 1/2. Its superpartner has a spin of 0. And similar thing for the others. Why this supersymmetry is especially appealing? Because, and I just repeat a bit what John mentioned before, it is that the lightest supersymmetric particle that probably is the neutrino, this lightest supersymmetric particle cannot decay in anything else. So it should be stable, and it is an excellent candidate for the black matter we are looking for in the universe. Let me move now to more experimental aspect. If you collide two protons of 7 TeV, so with this fantastic kinetic energy, what you will get? You will get 1,000 of particles. These particles, if you can materialize the tracks, and if they are inside a magnetic field, all charged particles will make circles. The circles is a way to measure the speed or the energy of the particles. And it is this type of things that you could visualize if you imagine a plane perpendicular to the line of interaction. The important message you can get from this plot that there will be many particles produced. And when you have so many particles, one of the first goals should be to have an excellent granularity in your detector. Granularity, it means should be capable to separate two tracks which are a few microns apart, one from the others. The detector of the LHC should also be capable to hold quite level of radiation. So it must be almost radiation hard. The third important property of the Large Hadron Collider experiment is that the response, the time of response of the signal should be extremely fast. But I don't want to go into too much detail for that respect, but it is clear that the machine itself is a technical challenge, but the experiments is or has been for long even more challenging than the machine. Anyhow, the physicists have been enough inventive, they have developed new technology, and now everything is well under control. We have just to put them together to build the LHC detector. An example is the Atlas detector. I don't want to go in too much details. Probably the first very important point on this drawing, it is a man or a woman, we cannot see from there, which is about, you see, just gives a scale. In other words, the Atlas detector will be something like a 40 meter or 45 meter long, and I can't remember exactly, something like 15 meter high. I don't want to go in all detail, except if you have questions afterwards. It just shows the complexity. So these detectors are really something which go beyond what any laboratory in the world can really build. That's why to build these detectors, we have big collaboration were absolutely needed. These collaborations, in the case of Atlas, involve 34 countries, 151 institutions, and 1,700 scientific authors or physicists. It just gives you a feeling of the necessary resource we have to find in terms of force, in terms of manpower, in terms of money, to build this gigantic detector. The other LHC detector is CMS. It is the same principle. I don't want to go into detail. Let's move now to the third LHC experiment, which is called LHCb. So LHCb is an experiment to look for new physics through CP violations in B meson decay. What does that mean? I'll try to explain in simple words. First, let me come back to the well-known drawings from atoms to quark, where you see, so well, an atom, you have the nucleus, you have the electron all around, and in the nucleus you have protons and neutrons, and the proton is built of quark, and two quark up, down. You have other types of particles, of other types of proton in a way, the ones which are called lambda, which are composed of other type of quarks, and this makes the baryons. Now, if instead of 3 quarks, you have 2 quarks, you build some objects which exist that we use in our laboratory, which are called mesons. And there is actually 3 types of mesons. The pion, made from a U quark and a D quark. The kaon, made from a U quark and a S quark. And the B quark, U and B. What is especially interesting, that the U quark and the D quark have a mass which is very close to 0, while the B quark has a mass which is something close to 4 GeV. So the B mesons have a mass which is quite large, and this is very helpful to make some measurements. Remember, for LHCb, there were 2 important words, B meson and CP, CP violation. What is CP? It is the operation where you first permute all the charge, conjugational charge, and P, it is a parity where you just, for each event or each particle, you take its mirror image. In other words, you permute the left and the right. We know, and one of the very important things we have learned looking at on the history of the universe and how the matter has been formed after the Big Bang, that at the end, if we are here, it's because the matter has won on antimatter. Initially, at the Big Bang, there were as many matter as antimatter. And if it would have been the case, we would not exist, because when matter meet antimatter, they just make just radiation. They don't stay in a stable way. We have also some measurement, we have some guess on how large was this CP violations when the matter relay win over the antimatter. And this is just counting the number of baryons and number of photons which were in the very early universe. We know that the CP violations is quite small, so 10 to minus 9, 10 to minus 10. It is something which is absolutely essential, and I guess Pierre Binetui will come back on that afterwards, on the history of the universe in cosmology. And we would like to understand it first at the level of elementary particles. However, the CP violation, which has been studied and discovered in laboratory, cannot be explained so far by the standard model. So they are not sufficient to explain this difference between matter and antimatter that I mentioned before. Interesting is that it could be another reason to find new physics, that the supersymmetry, there are much more particles, all the superpartners, and it could be a way to generate a new source of the CP violation. So it is this physics that the LHCb will address, CP violations in the B meson decays. And why is the B mesons? Because, as I said, they are heavy, and because they are heavy, the effects are predicted to be large. So they are well identified, and what we would like to see, hopefully, that we will not observe what the standard model predicts, but something which is different, which should be another way to access the physics beyond the standard model. And why at the LHC? Because the LHC, you have a lot of energy in the collision, and you produce many bosons.